the rule I couldn't remember, it's called Hund's rule. So what you have to do is you have to fill a subshell before you go to the next subshell. So you gotta make sure that there's, that each one of the orbitals is filled up before you move on to the next one. Alright, looks like he has easy stuff. We got quantum mechanics. Give me a degree in quantum mechanics. Okay, beryllium has how many electrons? It has 4. Okay, so it's Alright, chlorine has 17 electrons. Two, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 14, 15, 16, 17. Okay, and magnesium is 12. Okay, so there you go. All right. All right. All right. So let's study this. Okay. All right. So there's a lot of information here. Now, one of our goals is that one of the goals of doing all this is, I said, if you know the structure, you can figure out the function. Okay. Well, we have structure. How then, if that's the case, can we figure out our function? What are we shooting for? Well, one of the main things we're shooting for is oxidation reduction. How things gain and how things lose electrons. And that has something to do with this. So this is going to help us figure that out. Okay. Now what we have is how the electrons fall into the atom. So they just don't all line up, just don't fall randomly all over the atom, but they end up falling in very precise places in these diagrams, and that will help us figure out the behavior of our atoms. Now I picked out these four guys to help explain that, okay? Now, a couple things about it. First of all, if you treat this as an actual visual, we can get some things out of it, okay? All right. So for this guy right here, I don't even need this, all right? This is the outer shell, or the outer energy level. I'm going to use the word shell, and that's going to be equal to energy level, okay? All right. So this is the outer energy level. So this level right here interacts with the world. Okay, I don't know, if you want to think about it, it's out here. Okay, so this guy interacts with so this is the outer shell. Okay, let me tell you a story. So, very long ago, at a time long ago, in a place far, far away, I lived in Ann Arbor, and so my wife at the time, and she says, let's go shopping. And I go, what? Like running shoes? She goes, curtains. And I go, I have to. She, come on. And I go, okay. So I go shopping. I'm not shopping. If there would have been cell phones at the time, I would have been watching a football game, right? And I turned into a 5-year-old, you know. And so I dragged my feet and she's, what do you think of this curtain? I go, it's blue. Okay. No, what do you like it? Yeah, I like it. Okay. And so, and then she comes up and goes, we need some New Balances. And then all of a sudden I perk up. I go, what? Balance? And she was there, the curtains that go on the outside of the curtains. And I go, that sounds a lot like chemistry. That sounds like valence. And I thought to myself, it wasn't telling. And click, it made sense. Why? So there's the outer shell of an atom is called the valence shell. And why is it? Because it's a curtain. It's the outside, it's sort of like, it's the curtain of the atom. Okay, so that's why they call it the valence shell. It's the valence, it's the veil, okay? So this is called the valence shell. The outer shell is called the valence shell. And that's the thing that's interacting with the world. The valence shell is the skin. Okay, it's the thing that's being bombarded by the world. It's interacting. It's the interaction of the atom with the world. Okay, it's one of the interactions. The electrons in it are called the valence electrons. Okay. So fluorine has energy level 2, it's a valence shell. And how many valence electrons does it have? 1, 2, 3, 4, 5, 6, 7. Okay. All right, let's look at beryllium. Okay, beryllium, we want to figure out the same stuff. What is the skin? Okay, it's energy level 2. So energy level 2 is valence shell. How many electrons? It has 2 valence electrons. All right, chlorine. What's a valence shell? 1, 2, 3. It's energy level 3. It's a valence shell. And how many valence electrons? 1, 2, 3. 7 valence electrons. Okay. And magnesium has 2 valence electrons, and so it also has energy level 3. And it has 2 valence electrons. Okay. So I picked these 4 on purpose to talk about, try to get the point of function and structure. Okay. Let's start out with chlorine and fluorine. Chlorine and fluorine both have 7 valence electrons. Okay. If you notice where they are, they're in the same column. Okay. Fluorine and chlorine have something in common that we learned way long time ago when we were talking about ions. What's the charge on fluorine and chlorine when it's an ion? Negative. So -1, or 1 negative, okay? So that is a chemical property. One of the chemical properties of fluorine and chlorine is that it has a 1 minus when it's an ion, okay? If you notice, they have the same number of valence electrons. So it turns out the number of valence electrons is associated with that charge. And we'll talk about that down the road. Okay? But, so, elements that are in the same column, who was the guy that came up with this? Mendeleev. Okay, when Mendeleev came up with the periodic table in the 1800s, he knew nothing about the electronic structure of the atom. What he did was he paired up, he put electrons in rows according to their weight. He put the elements in columns according to their properties. So the elements that are in the same column, they have very similar properties. If you notice that fluorine and chlorine both have the same number of valence electrons, okay, and they have similar chemical properties. So it turns out that the chemical properties of an element are associated with number of valence electrons. Okay, that's big right there. So if you notice, we were able to figure out the number of valence electrons. We're able to come up with a structure. We got some more. We have structure, we have function. We're able to figure out a function based on structure. Now we haven't told why it happens, but we see that there's a relationship between the structure and the function of an element. Okay, if you look at magnesium, beryllium, what are their common charges? 2 plus. And if you notice, they have the same number of valence electrons, all right? So number of valence electrons tells you something about the chemical properties. Okay. Now, also if you look at chlorine and fluorine, is that, okay, fluorine, so all the elements in, well, remember that video I showed you of them taking the different metals like lithium and potassium, then throwing them in water, and they go kaboom, okay? And there was, then they took lithium, put it in water, you got a little boom. Put sodium, you got a little bigger boom. You put potassium in, you got a bigger boom. You put rubidium in a bathtub of water, then went kaboom. And then we put cesium and it blew up the whole, it blew up the, blew the tub up. And then francium, they show up a big blowing up in the ocean. Okay, each one of those guys have one valence electron, but what they do is so that's their chemical property, is they react with water. They become oxidized and they lose one electron. They have different abilities of that chemical property. Francium has a really high ability to do that, while lithium has the lower, but they do it all in the same. All right. If you notice, the ability of a chemical property is determined by the size of the atom. Okay, francium has a different size than lithium. Okay, if we go on the other side of the periodic table, it's the same way. Okay, fluorine, we talked about. I told you, fluorine is the big is the guy that's going to reduce everybody. I'm going to get reduced. Okay, it's going to go around steal electrons. It's the boss. All right. It does it better than anybody else in that column, and that's because of its size. So what you have here is two different things. First of all, you have the number of valence in the outer shell sort of determine what it's going to do, the chemical property it's going to have. Then the size is going to tell how well it does. Okay, so those are the two things we're going to end up talking about when we end up figuring out all this in depth and trying to figure out things. Is that you're going to look at the number of valence electrons, and that's going to help explain chemical properties, and how well it does a chemical property will determine by the size. So we'll end up looking at two things: number of valence electrons and the size. And what is the size determined by? The number of energy levels. Bit more energy level, the bigger it is. Okay, and vice versa, smaller. So we're going to tie that all in. Okay. All right. So for the orbital energy diagram, OED I call it, you're only going to have first 18 elements. You know, we can do it for more and more and more, but we're going to see that the next wave we're going to portray the model of an atom will help us. So it'll be a lot easier to figure things out. So on a test, I will say, well, give me the orbital energy diagram for silver. And you go, Scully, you told us we couldn't do that, all right? Because silver is number 47. But if I say, do the orbital energy diagram for oxygen, why don't you do that right now? Let's do the orbital energy diagram for oxygen. Then you should be able to do it. So just take a look at it. And find out how many valence electrons and how many energy levels. And then see if you can see a relationship between its common charge and its electronic structure. right, so oxygen, and it has, the valence shell is energy level 2, and it has 1, 2, 3, 4, 5, 6 electrons. Okay, now, the common charge for oxygen is 2 minus. All right, how does that relate to a structure? Well, if you notice here, there's 2 empty spots. And we're not going to, just notice it. And don't try to make any kind of leaps of faith on this, okay? 2 minus means it's gained 2 electrons. Okay, where do you think it's going to put them? Right? Right there. So, and we'll talk about the Y's and stuff like that down the road. But, so you can see that, and that's a chemical property of oxygen, is gain electrons, and it can gain up to 2 of them. Okay, it could gain 3, or 4, or 5. Okay, but it typically only gains 2, and we'll talk about that down the road. Okay. All right. So, so we can do the orbital energy diagram for the first 18, and then for the other ones, I don't want to draw that. I want to be able to make it concise, but I know that I can. I'll show you, we'll be able to see how that works. Okay. All right, now the next model we're going to talk about is called electronic configuration. And so the difference for the orbital energy diagram, it includes the energy level, it includes the subshells, it includes the orbitals, and it includes the electrons and their spins. It includes everything, okay? So that tells me, so it has energy levels, it has subshells, it has orbitals, it has electrons, and it has spins. So it has the whole gamut, okay? For electronic configuration, what we're going to do is get rid of some of that information because we know it's there. We're going to get rid of the spins, we're going to get rid of the orbitals, and we're going to keep the number of electrons and the subshells and the energy levels. Okay, so if we look over there, so energy level 1 has an S subshell, energy level 2 subshell, and energy level 2 P subshell. So what you do is you write those down. So you write down 1S, 2S, and 2P. Okay. And then what you do is you write how many electrons are in each subshell. So you have 2 here. And then what we do is to make it a superscript. Okay, it's not square, it just means there's 2 in the S subshell. Okay, there's 2 in this subshell. And then there's 1, 2, 3, 4 in that subshell. Okay. All right. So this is the electronic configuration for oxygen. And we got it from this way. Okay. What's the valence shell? By looking at this, well, what's a higher number? 1, 2, or 2? 2. Okay, so the valence shell is 2. How many electrons are in those 2? 6. It's not 4. Okay, it's not 4. Because there's 2 here, they're both, this is the energy level 2, and there's a total of 2 and 4, so there's 6. That's a mistake that people will make. They'll just look at this N number, and they'll say that's how many valence electrons. So you have to look at the front number. Okay, so now let's look back at the other ones you did. So let's do fluorine, and which you did already, and magnesium. Okay, You guys have it written out already, so I'm gonna redraw it. Okay. So what I'm gonna do is I'm gonna circle the subshells. Okay. So don't just circle the individual orbitals. And then write down what they have. 1s, 2s, and 2p. Okay, then you have 2 here, 2 here, 1, 2, 3, 4, 5 there. Okay. And that's a valence shell, and how many valence electrons? 7. Just like we said before. So if you notice what we're doing is we're getting rid of the arrows, and we're getting rid of the little boxes. Okay, this guy over here, so 1s, 2s, 2p, and 3s are the subshells. You have 2 here, 2 here, 6 here, and 2 there. Okay, what's the valence shell? Number 3. And how many electrons? 2. Okay. Okay, so you can get this guy. You can get maybe okay. You recognize this thing? No. No. But is your own page? Oh. Yeah. All right. So it's periodic table. Okay. What I'm going to do is I'm going to do some chemistry origami. All right. So this is really complicated. What I want to do is I want to fold it up. So I'm just going to. I just want to look at the first 3 rows. Okay. And so what I'm going to do is I'm going to fold it up so it just represents the first 3 rows. Okay, so I'm going to fold it like that to get rid of the rest. Because that's what we're doing, what we're going to do in a second. So fold it up like that. And so you can do this at home with your kids and your little brother, okay, or sister. Then what you do, carefully, you fold it up so that number 4 lines up with number 5. Okay? Pretty cool. All right. See? All right. Okay. Okay, the other thing I'm going to do is I'm going to move the helium right next to the hydrogen. And that's okay to do because if you draw it, it has the same electron configuration. Okay. So what I'm going to do is I'm going to take this diagram right here and I'm going to flip it. So 2, 3, and then I'm going to split them up and put an up arrow here, down arrow here, and so forth. Well, if you look at these two, they're almost identical, all right? You have the hydrogen, helium, the lithium, the beryllium, carbon, nitrogens, and so forth, all right? So the periodic table has the orbital energy diagram in it, kind of. It doesn't work completely, okay? But so if let's say we want to know the orbital energy diagram for boron, okay? Well, where's boron in the periodic table? It's hydrogen, helium, lithium, beryllium. So this beryllium, well, it has 4 electrons. There you go. Okay. So the periodic table can actually, looks like it can give us the orbital energy diagram. All right, it has the same information. Okay, it does. All right, and but it's not, we can't, there's not complete connection here. But they have the same information, a lot of the same information. So what we can do is that you can also get the electronic configuration and the orbital energy diagram from the periodic table. And that's what we're going to do now. And this is a method, and it's more of a method, but the method is because the periodic table is built the way it is. All right. So the way you got to do this is we got to look at the periodic table and see how it's split up. Okay. It's not just randomly. It's not just random. All right. Now, okay. If you look at going up and down vertically, you can see that it has sections. Over here is a section. Over here is a section. Over here is a section. And this section right here is actually